Homework, good, cool. Just finish that Jupyter Notebook and upload the Jupyter Notebook and just upload all the outputs to Grayscope. That's it. I guess just for you to get a sense how we process music files in on laptop, and you can sort of imagine like from there there's still a lot of things, but once you can load them into like machine readable format, now you can do all the, if you want to do machine learning, if you want to do data science, you want to do just analysis, you want to do all sort of different tasks, then that's sort of the way how you start it. And the next PA will be on audio. So after today, um, and I should extend the deadline. Oh, the deadline will be after next week. So next week I will be traveling for a conference. Um, so we don't have class next week. But PA2 will be due next Monday. Cool. Yeah, just a quick recap. We've been basically talking about how you just represent music and audio on your machine. We pretty much go over everything. The remaining one is just the image one. So, MIDI, this is sort of like what you are doing in PA1. But you also do something as piano roll in PA1, because that's pretty much, once you have the symphonic music, it's just thinking about how you represented differently because they are equivalent, sort of equivalent representation, just that you need to process a little bit. But most of the time, you don't want to rewrite everything. You just call the package. But you could probably guess, inside the package, it's just doing all sort of, you can turn this MIDI so from Note 60 from time shift 2. So you can sort of imagine where that is in the piano roll. And that's how you get that piano roll out. And waveform, we talked a little about it last week about, digital sampling rate, stuff like that. And we will continue and finish the spectrogram part. And we will have that in PA2. Cool. And we talk about this ABC notation, very simple, but it's very limited. And we talk about MIDI message. Likely you will see it in PA1, even though PA1 is using a slightly different representation where you have the note rather than, each single. So the difference between the notation we are using in PA1, that's the muse file, and this MIDI message is that, MIDI message, you have to have like three things combined together so that you get you get a note. But in MusePy, each note is itself a row, an object, basically, object-oriented music language, I guess. And we talk about piano roll. It has some history. It's a physical thing, just that it could also be a representation. Cool. And we talk about waves, but I guess these are just reminding you that, even though you see this, but it's actually a pressure wave rather than, it's just representing the high pressure and low pressure. Cool. And we talk about human ears. I'll just skip. And we talk about the inverse square law. And we talk about this equal loudness curve contours, which is probably the most basic thing, so that, human ears are sensitive to certain pitch range in the middle range, around 3K, 1K to 5K-ish, and then everything else will just decay and become less sensitive. And yeah, today we're talking about spectrogram. Cool. I think we already talked a little bit about that. We somewhat stopped somewhere here in the sampling theorem, and I think I forgot to mention the one important word is Nyquist rate. So last week we talked about, you want to critically sample a signal properly at the certain sample range so that you can reconstruct that frequency. It's important because, when you are using a telephone, like old school telephone, it's only 8K hertz, like 8,000 hertz, then the maximum frequency you can get is 4,000 hertz. And so pretty much all the harmonics, all the timbre is gone for my voice. So that's why, in the past over the telephone, it's very hard to, actually recognize who that is without, knowing their numbers. So Nyquist rate is basically two times the original frequency, and that's what you need for the sampling rate. So if you want to capture a sampling rate of like 10,000 hertz, you need 2,000 hertz. At 10,000 hertz, you need 20,000 hertz. If you want to capture 500 hertz signal, then you need 1,000 hertz sampling rate to capture that. And the reason is that, just look at this, when you're oversampling, it's much easier to just reconstruct that. Look at all the red dots. That's the digitized, quantized or sampled audio. So, without looking at the blue lines, looking at the red lines, you can still probably guess what that shape is. But when you are undersampling it, like in this case, if you look at the red ones, how could you guess that's just the blue one? Because, for the model, it could just say, I would just connect them and assume that's the maximum frequency that we have. So this is pretty much the intuition behind sampling theorem, where you need, dense enough sampling so that you get to reconstruct the blue one. And the same for this. So pretty much what you need is that critically sampled, where you want all the peaks on the positive side and the lower side. So that will be two times the original frequency. Yeah, so these are just intuition to show you that why sampling theorem is the case. So what is the maximum frequency telephone audio can capture? If telephone is like 8,000 hertz. Yeah. So for 1,000 hertz, like as I talk about like the pitch, so when we are singing, sometimes you could reach that sampling rate. So that's somewhere we human voice can still reach. So it's almost at the boundary of how human can sing the highest pitch. So pretty much telephone audio is just that. Well, we just do that because in the past, telephone is it's like the highest bandwidth that we can do is 8,000 hertz. So how about to cover the human hearing range of 220 hertz to 20K hertz? What's the minimum sampling rate required? Oh, yeah. And that's actually why we now have all the 44.1 and 48K hertz, because that's just slightly above 40K hertz. So there's also some reason, why 44.1, because people always ask, like, why 44.1? It's just like so random. But basically, they want 40K, but slightly above. And so somehow, and they pick, I don't know why, but they pick 441. But nowadays, usually people are using 48, 96, 192, especially when there's like the DVD video base, which is 40K, multiples of 48K hertz. For audio, CD is 441, and everything else is like 96, 192, 384. But anyway, there's a reason, because you want to sort of like cover the human hearing range, which ends somewhere around 20K hertz. Cool. So this is like the frequency range that we have. So this is the original, like 1934 Bell Lab. So Bell Lab is like sort of where they invent the telephone, and then all the early audio research being done at Bell Lab. So this is like 1934. They are starting to see where are our human hearing range. So this is how you look at it. So these part is like where music will typically lies in. So this is the sort of like music frequency range. So it's not much, like slightly larger than the speech frequency range. So when you're designing the frequency range, you look at it like it's like ends at 4K-ish, and that's why you pick the 8K hertz for telephone. Then you can pretty much cover the whole speech range. But for music, sometimes you will get, much higher note, especially a violin, or you think about the highest pitch on piano, then it's sort of like correspond to 10, almost it could reach 20 if that's the human range, but it could reach somewhere like 10K hertz. So if you want to do music, then at least you need 20K hertz to just, faithfully recover all the frequency that it covered. But still, nowadays people are using 44.1 because that cover pretty much the whole human hearing range. Question on this? I guess just almost feel like fun facts. But that sort of have some reason behind some of these specific, like overly specific sampling rates. There are some reason. Cool. So I guess the rest of this class, we will just go over the spectral analysis, and that will be the key of homework two. So the goal is pretty much go over Fourier transform and short-time Fourier transform. We won't go into the math, but hopefully after this, you can sort of get a sense of what's going on about Fourier transform. And I think it's important because sometimes I met with someone and they are using STFT and they pretty much just treat them as image. It's fine. I mean, you can treat it as image, but at some point you should just dig into it and get a sense how this magic thing happened. Cool. So spectral analysis, like all the Fourier transform, you see the spectrogram, stuff like that. It's like feel like a magic, but there's some, underlying principle and underlying math formulation that how you get those. But pretty much our goal is just to analyze the frequency components of signal. So as we talk about, when you listen to when you record an audio, it's pretty much just measuring the pressure wave. So something like this, but these are the pressure wave, like high pressure, low pressure, but pretty much it's just a fluctuation between the pressure. But that doesn't tell us what the frequency components of the signal is. So if you look at this signal, it's actually combining two signals. You can roughly see the shape. So you have this 2 Hertz signal. So if you look at the x-axis, it's like 1 second and it repeats 2 times. So that's 2 Hertz. And there's another like 10 Hertz thing going on. So if you combine these two signals together, you add them up, you can actually get this original thing. So the idea of spectral analysis or Fourier transform is trying to go from this and directly you want to get sort of like, what are the frequency components? Can you just apply some math, then you decompose the original signal into certain, signal, the combination, the linear, weighted sum of these different frequency components. So that's exactly what spectral analysis wants to do. So if you look at it, this figure, this plot is given by, this whatever sine wave, but it's being composed by two different sine wave with different frequency. One is 2 Hertz, one is 10 Hertz. And now if you look at another case, this case, now you can still feel like there's something going on with the 2 Hertz because it goes up and down, goes up and down. So now things become much trickier, but at least, there's some 2 Hertz. And then you can look at the peaks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know. So you pretty much see, whenever your frequency components become more complex and complex, it can be tricky to see what are those components. So there's actually a 5 Hertz component hidden in it. It's much smaller amplitude, but there's also a 10 Hertz things going on. And that's why all the tiny fluctuation. And sometimes, these up and downs will be hidden by this bigger wave of 2 Hertz. So that's all the challenge about, why it's not a simple thing, why we need Fourier transform. Because, if you just look at this and think about, well, let's just count the peaks and, dips, you can pretty much guess where those are, but it's not the case because, if this signal is much smaller amplitude, it will be, sort of like hidden into this 2 Hertz thing. So we need something to do better. And that's what Fourier transform comes in, even though if you look at the mass of it, there's no way we could tell what's going on here. So in the next few slides, I want to just go over what's the intuition of it. And this form is just a very beautiful way to represent that intuition into a mathematical formation. So when we are looking at this, what we want to do is go from this FT to this frequency domain. So this omega is basically the frequency, even though it's slightly different. But what we want to do is go from signal to spectrogram. And what we want to do for the other stuff we will go over that. So sum over t, and this is the weirdest thing that we should look into it. So pretty much, this thing is just a fancy way to represent a combination of cosine and sine in the complex form. So this actually turns into this. So whenever you see the Fourier transform, it will usually look like this, sometimes look like this, but they are equivalent. But now going on, we will forget about this formula, and I will tell you what's the intuition behind it. And at the end, these intuition together become this, this formula. But at least what you can see here is that, well, now we are doing multiplication between our signal with a certain frequency of that. So what we are going to show next is that how we decompose, how we detect a frequency. Does it exist in that signal or not? So take this things, for example. I don't know why there's a line, but take this thing, this signal, for example, and think about, what we are trying to do now is not about, it's not about just look at it, stare at it, and we get all the frequency component, but rather we have all the different candidate frequency components. So from 1 hertz to 10 hertz, for some different frequency. And so now what we were trying to do is that we grab 1 hertz and try to see whether it's inside it. So how are we going to do it? So we grab this 1 hertz and then put it on top of this signal. And now what we are trying to do is to see whether this thing has this component is to see, as we said, you see that there's this like going up and down, going up and down. So that pretty much is the intuition here. When you do the multiplication, when they have the same trend, they should have positive value with their multiplication. So now what we are going on in this plot is that for each single point, you take the number of this, the red one and the blue one, and you times it together. So at the beginning, these are all positive because they are both positive. But now between this part, one is positive, one is negative. So together they become this, lower dip thing. And in the middle, both are sort of like zero-ish. So there's nothing here. And now here they did a match. So it's a negative. Now they both are negative. So they are positive. So you get a sense that, when they are both positive, for this plot, it will be positive. When they are both negative, they will also be positive. When they didn't match, then it becomes negative. So pretty much, this plot, when you sum it over together, like sum up all the, blue part and the red part, if everything is positive, then we are happy. There's some frequency inside that. So in this case, it doesn't match because if you sum the whole, positive part and the negative part together, it will sort of like cancel out. They are like equal amount of, positive and negative. So we won't call it a match. But now, we know there's something going on here in 2 hertz because we can visually see it. Now, if you plot this, then you get all sort of like all positive thing. Because, whenever the red one, the only part that's not positive, there's some slight, small, very small negative part here. That's just only when they did a match. Like one is negative, one is positive, one is negative. But pretty much all the other parts is like both negative or both positive. So, by just slide things through, passing this 2 hertz on top of this, and then you just compute, the multiple between the two signals, then you get this curve. And whenever everything is positive, or, at least it together sum up into something, higher in its positive value, then it's a match. And now you can just basically just go over all the frequency, candidate frequency. So 3 hertz, you go to it, and then you see that, well, sometimes positive, sometimes it's negative. So this pretty much just cancel out. And then the same for 4 hertz, pretty much cancel out again. But now, 5 hertz, now you see that, well, now it's a little bit trickier than 2 hertz. It's not always positive, but for most of the time, it's positive. So if you just, take all the blue areas minus the red areas, you get a smaller, smaller sort of like detection. And so that's what we'll see later. That's how you detect how much, how strong that component is. And then for 10 hertz, now it's again, there's like positive and negative, but overall there's a match. There's more positive than negative. So that's actually what's going on here. So if you look at the thing, you have the ft times the cosine, some wave. So that's essentially what's going on here. And there's, however, another component, which is like ft times sine, and the same frequency. And there's this j, which is the complex thing. But the tuition here, actually, that's not what I want to talk about here. Anyway, we'll get into why there's a cosine and sine later. But pretty much what you're seeing here is that, pretty much you just get these two things and then you take their multiple together. And then now there's this sum over OT. So that's essentially what Fourier transform is doing. This is the integral. So basically, when you are doing integral, meaning that you go from this end and to this end and you sum it up. So now Fourier transform is exactly what I just talked about. You take two signals and then you multiply them together, and this is the multiple, and then you sum over t. And we will get into this other term later. So this is pretty much Fourier transform. So as I said, we have multiple candidate frequency, and that's how you get this. So you go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and everything else that become a smaller, the amplitude. So you get 2 hertz, and then that's how you get that very high peak. And then you do 5 hertz. Now, the sum becomes smaller because there are some negative. And for 10 hertz, it's much smaller because there's more negative. But general, look at these two big, blue area. So pretty much it's still sum to 0.1. And for everything else, pretty much the blue and red part just cancel out. Yeah, so that's pretty much what we have. So now if we look at the other term, now we have this cosine term. What's going on is that now it's still doing the same frequency, just that, when we are looking at sine wave, it starts from 0 and go up and down and go back to 0. Now the cosine start from 1, go to 0, go to the bottom, and go back to 1. So sine and cosine is just the same signal at different places. So that's what Fourier transform now become much more complex. Now you are looking at, this frequency, and it doesn't always match the original frequency where it starts going up and going down. So now if you look at the same, 2 hertz, now if you use the cosine, then there's no match anymore. Only when you start from 0 and go up and go down and back to 0, you will see that match. So the whole things here is just trying to capture the fact that this frequency component could be at different position. They're slightly offset, and we want to move it around to see whether there's a match. Cool. So this slide just want to show you that now when we take a cosine, unfortunately sum to 0, nothing there. But when you have a sine, that actually gives you that. So this is what we call phase. So phase is about the where the sine wave started. So this one is the sine wave. You see these are both a match. But now if you turn them into a cosine wave, now it becomes totally different. So in this case, it's a sine wave plus another sine wave. And let me explain a bit about this plot. So this is the signal, and this is like it's two components. And this is another signal. What we did is that we go from the sine to cosine. We didn't change the second signal. So the second signal is the same, but the first signal is different. Now you just move it for 0 point, move to the left for 0.12 second. So you pretty much grab here and then move it to 0. So you will get a totally different signal in this case. So that's whole, Fourier transform is about. You pretty much just move it around, but the signal just becomes something different. So the whole this J thing is just to capture that combination of cosine and sine. And you can actually put it into the complex sphere so that you capture all the things between cosine and sine. So you have a cosine signal, you have a sine signal, they have like slightly offset. And with this J thing, you can actually just cover the whole range from, a smooth transition. Think about you grab a 2 Hz signal and then you go from sine and then you slightly move to cosine, and all the way up, you are detecting whether there's a match. So that's the whole mathematic things going on here. So just a bit more math. What's going on is that when you started, you have this cosine. So this is the complex domain. Let's just forget about this. But this started from here. So this is like when you have the cosine when you started. And then now you move it around. So you move it around. Now this becomes like no cosine anymore, just the sine. So now you become this shape. And then you can keep moving around. So you can keep moving around. Now this becomes the negative cosine. So now you flip the cosine. And then you keep moving toward that. So now you become the negative sine. So there's a smooth transition from sine to cosine to negative, from cosine to sine to negative cosine to negative sine. And all of these can be captured by this formula, depending on how the real part and the imaginary part is combined. If it's like all real, it's like 1, 0, then it's just the cosine. If it's like 0, 1, it's just the sine. But you can think about this real and imaginary part is just to capture all the different combination, all the different possible position the signal could be. Questions? So that's the complexity over this. And, the whole Fourier transform, if you just look at one part of it, it's kind of simple, well, we grab a cosine and we assume that it's just a cosine. Then if we know it's a cosine, then we just take cosine and ft, the signal, and we multiply them and we just compute the area over it. And if there's a match, then it's good. But now the reason why we have this real and imaginary part is that we want to see where exactly that cosine or sine function is at. So we want to slightly move it to the left, to the right, so that we find a perfect match. And that's the whole, this real and imaginary part is doing. And somehow with the math, it can magically just sort of like cover all the different possible phase. That's what we call, like, phase is the position of this wave. And then you can do the detection parallelly on all the different possible x offset, kind of like time offset in some sense. Cool. So you can think about what the model is, what the Fourier transform is doing is that, well, you just go over the whole circle that going from the original cosine, and you just move for all the way through that. So you cover all the possible combination. Well, we can have another example. So what we have here is that, we have the same signal, which you have this sine plus sine, so 2 sine wave combined together. When you do Fourier transform, you see these 2 peaks. But now, if we have this, real plus imaginary thing, now we can, detect both cosine and sine, and they have the same effects at the end. So now if you go from the sine function and you move it away, give it an offset, when you do Fourier transform, it still show up here. And so even though they have the different waveforms, if you look at the Fourier transform will sort of like ignore not ignore the face. Face is another plot, but Fourier transform, when you look at the magnitude, it doesn't tell you where it is. It just tells you that there's a 2 hertz. I don't know where it is. But if you have to look into the face of that so that you know where it is. So that's one, interesting fact where, even two things has the same, Fourier transform spectrogram magnitude. It doesn't necessarily means that, you know exactly what the original waveform is because they could be slightly different phase. So when you move this signal to right for 0.5 second, it's still pretty much the same frequency, just that it's slightly off. Um, cool. Move on. Questions? Cool. Let's just move on, I guess. So if you have a 2 hertz sine wave, when you do the spectrogram, this spectrum just show you the magnitude without knowing the phase. But anyway, you will get this, a peak at two hertz. And now if you do 5 hertz signal, then you get a 10 hertz signal. Now you get a peak at 10 hertz. And so, you also see that, for something like 9.5 hertz, you still get a pretty good match because you think about if you get a 9.5 hertz, pretty much most of the time it match. Just it's somewhere in the middle, it doesn't match. So it's not always, it's not possible to sort of like get a perfect, peak at 10 hertz. Usually somewhere slightly around 10, you will still get a good, match. And so now, if you have a 10 plus 2 hertz sine wave, now you get 10 and 2, and you see their components here. Cool. So some more signals just to get you the sense. So the difference between this and that is that, well, this is like 2 hertz, but 10 hertz signal will be half the size of the 2 hertz. So you pretty much still see the 2 hertz thing. And then there's, additional fluctuation caused by the 10 hertz signal. But now if you increase the magnitude of the 10 hertz signals, now it becomes a little bit tricky because the 10 hertz one will sort of like make much larger fluctuation. But still, you can do that. Cool. So pretty much we've done with Fourier transform. So again, what's Fourier transform is just trying to detect the frequency components of a signal. And how do we do that? So we just go through a bunch of different candidate frequencies. So 1 hertz, and we just pass onto it. We compute the multiple. We just multiply them together, and we compute it whether they have always a positive match, because positive means that they have the same trends. If it's like going up and going up, then it will be positive. Going negative and going negative, it will be negative, negative. Still, the multiple will be positive. When there's not a match in different trend, then you get a negative value. So you just sum it up through the whole signal, and that's the way how we do Fourier transform. And all the, J, cosine, sine thing, it's just about thinking about how you horizontally move that signal around to find the perfect match so that your algorithm will be robust to, the different position of that waveform. But you can still detect the frequency rather than being fooled by just a slightly mismatch in the offset. Cool. So that's Fourier transform. And in PA1, we won't be, implement Fourier transform, but you will get to try it. So you will just do Fourier transform on some signal, and you will get to see, some of the this thing. Basically, you get a waveform, and then you can just analyze the spectrum. So pretty much, there's no way we can actually compute this. Unfortunately, we cannot compute this Fourier transform. We can compute by hand. If you know that it's a sine wave, we can compute by hand. That's all the signal processing course is about. But on the computer, as we talk about, there are sampling rate, there are quantization on the both the temporal and the amplitude part. So we have to deal with the fact that, well, our signal is no longer perfectly continuous. There is some sampling rate. So that's the whole discrete Fourier transform is about, where we are doing Fourier transform with discrete time and frequency. But we won't go into detail. But the idea is that, well, we still want to do Fourier transform. But now, because our signal is digital audio, we cannot achieve an infinite sampling rate. So this is the formula. Again, now it's still very ugly, but it's pretty much the same as the Fourier transform. It's actually quite beautiful. If you stare at it for a while, it's just how elegant it is. Just at the first time you see it, it's like, what the hell is going on? But this is pretty much the same as Fourier transform. So you have that exponential thing, so it will divide it into cosine and sine. So it's pretty much the same thing, just that now you are doing one point by point multiplication rather than doing that summing up thing. You still do sum up. So this sum up from n by 0 to n minus 1 is pretty much going from t equals 0 all the way to the last point. And then the thing is that, well, your input signal, and then now you are timing different possibility of cosine and sine, just that now it becomes digitalized. Cool. And that's the FT, discrete Fourier transform. And in practice, we are using this very cool algorithm. It's actually one of the top 10 algorithms from the 20th century. So you see how important this algorithm is. Other than FFT, I think all the other algorithm is what you were being told in algorithm class, but FFT is in signal processing mostly. But basically, you can actually lower the whole DFT thing here. If you want to compute this, originally you need n squared, but you can actually lower it down into n log n. It's very cool. And in one of my signal processing class, I have to do it, but we won't be doing this. But it's a very elegant implementation of discrete Fourier transform. Cool. So that's Fourier transform. So, one of the biggest question is that, well, now we have this recording. How can we get the spectrogram? So let's take a listen. What is this? I think this is what we will be working on the homework. And as usual, there's no sound. Let me try again. And the magic is that whenever I read. Okay, it isn't this. Let me check. Should have. So. Okay, anyway, I don't think we will be playing a lot of audio today, so I will just play through my laptop. Cool. That's it. So you have this signal, and now if you apply Fourier transform, this is what you get. So you actually get this kind of shitty and spectrum. So what's going on here? Any thought? Think about what we just talked about and why it doesn't work here. Why you get all these stuff. So this is what we have. Why? Oh. Is the frequency the same at the beginning and the end? So there's a question about Fourier transform, right? Because when we talk about Fourier transform, you grab this like 5 hertz and think about in this case, say the first one is a C, it's a 440 hertz, then you start from there. And then you just look at this whole thing and then ask the question, is there a 440 hertz in this signal? And the Fourier transform would just say, yeah, there's something here, but there's nothing over there, over the other part. And that's the same case over there. So if you look into this spectrum, it's pretty much just messing up all the frequency together. So if you if you zoom into it, you will see that actually there are like 6 different nodes, right? So all those 6 nodes, the frequency is actually being captured here, just that they are just like clustered together. And there's no way you can localize where that frequency is. And so that's what we are going to talk about next, showtime Fourier transform. Basically, can we do something so that we can localize, where that 440 happened here, or that 440 hertz happened in the middle, where does it happen? And so that's the limitation of Fourier transform, because Fourier transform doesn't tell you where that frequency is. It just tells you that, well, this frequency shows up in this signal, but I don't know where it is. So the intuition is very, very simple. You just slice it and then you apply Fourier transform. Even though technically it's a little bit more complex, but for now, think about it that way. You just slice these audio into multiple slices. And so now you assume that, well, the frequency won't change properly. So at this slice, it's 440, 440, 440, 440, 440. And then now at the other part, it becomes another frequency. And so that's essentially what we are doing in this spectrogram. That's the SDFT. So, we talk a little bit about this. So, at the x-axis is the time, at the y-axis, the frequency, and you can see that at different position, you have a different magnitude. So when you are doing this, you pretty much just go from this, and then you grab this tiny slice of audio and you apply Fourier transform. And this slice is what you get. So it's a little bit tricky. I guess I should draw something here. So pretty much what you will get is n. So this thing is actually something like, oops, is it working? I hope you see what I meant. Things like this. So you grab this and, originally when you apply the Fourier transform, what you will get is that, well, now we find a pig and we find a pig, we find a pig, we find a pig. And so this is your spectrum and you turn it into vertical and put it there. And now you use colors to represent if there's a mesh. So this is the peak. And so this is pretty much one slice is the spectrum, just that now you turn it into vertical and then you use colors rather than the height of that. So pretty much still the same thing. And then you just go in through all the slices and then you do the same thing again and again. Let me see. So yeah, so you just slice through it and then you will see that they didn't match in time. You will see in the x-axis. But anyway, from 0 to 1 second, let's go through it again. So there are 6 nodes, and if you look at this thing, it just go over like 6 nodes. So first node, second node, da, 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 da. So there are like 6 different nodes. Cool. Let me get rid of those. Yeah. So actually, this is the what SFT is going on inside. So this is the intuition. You just slice it and then you apply Fourier transform. But that doesn't work quite well in practice because think about the border between 2 slices. So there could be something happening between the boundaries. So usually we want them to overlap when you do the slice. And when you want them to overlap, you also want it to be a smooth transition. And that's everything happening here. So at the top, this is the original signal. And so you grab part of it and you apply this triangular or hat shape things. So what happened is that, you grab this part and then you apply a fade in and fade out at the beginning and the end. So all these things that you grab out will have a fade in and fade out. But still, these two signals, when you add them together, it will be the original signal. So now you have overlap and you have fade in and fade out. But still, you're doing these things. So that's pretty much what SDFD is. And when you are working, when you're using the Barossa in PA2, pretty much the two parameters you might be wondering is window size and hop size. And so window size is basically this triangular thing. So what's the hat? It's triangular, but there are different shape of that. There's like hanging window, all the details. But usually, most of the time, we just use the default one. But anyway, something triangular, something like a hat. And the size of that is the window size. So that will sort of like give you the temporal resolution-ish. And you have this hop size. So, you have that triangle thing and you want to have some overlap. So the hop size will determine the overlap. And usually we set hop size to half the window size. So that pretty much half of the hat will overlap. So that's the default. But this just suggests that STFD, there is so many parameters. Most of the time you just do in PA2, it's like the Barossa, the STFD, and parenthesis, and you just put your signal X there. But still, if you look at the STFD page on Liberosa, you will see so many parameters there. So let me grab that. So this is the liberosa.stfd page. So you have like the signal, you have NFFT, you have flat hop length, that's the hop size, window hand. So this is the hand mean window. So we have so many different shape. So the triangular one is the much simpler one, but you have different window size. I should have a slide for that. Handing window look like. So you can have like different shape of windows. So there are different option of window shape. So this is the rectangular window that's without fade in, fade out. You have triangular where you have fade in, fade out, and hand window is usually the default one, which is smoother than the triangular angle, and it looks like a hat. So usually people call it hat function. Cool. But that's basically the same. Now just you have this fade in, fade out thing and the overlapping thing, but still pretty much what you're trying to do is just to go through all the slices and then you apply Fourier transform. So this is what you get on the Fourier transform, and then you turn it into colors rather than height. Cool. And so this is pretty much what you will get. So if you look at the y-axis, the maximum value. So remember the Nyquist rate we talk about. So the maximum frequency you can detect is half the sampling rate. So this in the Barossa by default, it used 22.5 frequency rate. 22.05. That's half the 44.1 hertz. So half of that will be somewhere around 11K hertz. So that's why you get the highest frequency here. So that's the maximum frequency you can detect. But it's a little bit tricky to see this. So if you zoom in and you see the 4,000 range, then you see all the fundamental frequency. So these is the when you look at the piano, what's the fundamental frequency, and you will have the harmonics. We'll get into that. So this is the this is essentially what this slide is for. So you have the fundamental frequency. That's when we talk about C 220, 440, or whether C is 440 or 432. All the debate about how you tune the piano. But anyway, that's the fundamental frequency we're talking about. And the harmonics would determine the timbre of that sound. So, when you play guitar, when you play bass, when you play, different instrument, why does the same C sound differently? That's because the combination of this harmonics is different. So I assume there's this. So, these are I'm not actually quite sure whether they are the same pitch. Likely, yes. But you can look at their spectrogram and you can get a sense that, they have a different profile of harmonics. So everybody has the same fundamental frequency, but the combination at the top is different. So piano, you see that over time, the higher frequency part will just decay. And for trumpet, it keep more. And violin, you see that vibrato. And for flute, there's a lot of like choppy part. That's because flute, you have a lot of like airflow. And airflow is not harmonic. So you will see those harmonics sort of like missing. So piano, trumpet. And so look at the at lower part, you couldn't quite see the vibrato, but at the higher part, you see the vibrato. And sort of the same for flute, but for flute vibrato, you are not essentially changing the pitch. You are sort of like changing the loudness, and you are combining airflow and the sound. And so that's where you see, some part of it is like there's a wide vertical thing. That's where you see that airflow sound. So, timbre is very tricky. It's not just about, the combination of the harmonics. It will determine sort of like the first thing you hear. But over time, how it decay, think about ADSR, how far does it need to get to that, maximum volume and then slowly decay, and how these harmonics decay differently. So in this case, the higher frequency part just quickly decay, but for trumpet, the higher frequency part doesn't decay that quick. So altogether, they create that, the timbre that you hear for different instruments. Cool. So that's essentially what we'll be doing in homework 2, PA2. So you are provided the whole notebook again, and you will have a lot of example at the top, and lower part, you will just do something based on what you sort of like learn through the first part. Should be pretty easy, but just to give you some tools that you can use. So look at this. This is what you get, and everything is very fainted because we actually usually represent spectrogram in decibel. So we talk about decibel. Decibel is log scale, where because our human ears perceive audio in log scale. So we feel like it's two times, 2 times louder is actually much more than 2 times larger in amplitude. So our human ears perceive things in decibel. And if you look at it, it feel like it's capturing what you hear, the relative amplitude of different components. So we'll get to this in PA2. Yeah, and we will go through sort of some of the things we see in class. And we will use this Liberosa, sort of the go-to package for doing the audio thing. There's a bunch more. You can also do B tempo things. So this is the like the most famous like the NumPy for MIR, so music information retrieval. You can do a lot of things. There's also different types of spectrogram. We only talk about the SDFD, but there are also, so many different ways to do this Fourier transform. And you have also other things. But anyway, you will get to work on the simplest part, FFT and SFT in Liberosa. Cool. I think we just finish this and then we can quickly look at PA2. So there's also some software you likely, maybe not likely, Opacity, maybe. But Sony Visualizer is more academic thing, so fewer people use it. But whenever you drag something into DAW, you see something like this. Either this is waveform, either something like this spectrogram, or if you have an Adobe Audition, you can also do this waveform view of that. So some DAW, you will definitely see it. And I should talk about this later. Cool. Let's just go to PH. Any question on the whole short-time Fourier transform thing? Nope. Cool. So this is PA2. Yeah, again, you would just go with it. Pretty much like PA1, now, but now we are using the Barossa and SciPy FFT. But anyway, load in audio. Essentially what we are talking about in class. And so if you look at it, it looks like this. So now you can use FFT to do that. So you can use SciPy.fft. We will go through a bunch of things. That's just the complexity of FFT. So when you do FFT, it's actually sort of like symmetry. You have like positive frequency, negative frequency. But if you think about positive frequency and negative frequency, they're equivalent. Like moving from the positive time with like 200 hertz is the same as moving to the negative time as 200 hertz because they match. So pretty much that's also why all the Nyquist rate. So you can think about you are sort of like wasting the other half of the frequency part. And that's why, Nyquist rate is 2 times the frequency, because half of the frequency is sort of like symmetry to the positive part. That's like an intuition. But you can sort of like imagine that could be the reason why there's a 2, the factor of 2. Not essentially correct, but that's how I sort of persuade myself. And you will just do a Fourier transform, and that's what we see on the slides, that everything just mess up together. So now you can do short-time Fourier transform, then hopefully it will be better. So now you get like localized chunks of localized Fourier transform over time. And you can actually show the phase. So this is the thing that I just talked about. So phase is like how these different components, whether it's like perfectly starting at 0 or it's like slightly offset. So the colors here meaning that, well, we detect this frequency, but what that frequency is detected at different, which position it was detected at. And so if you look at this, it's pretty much like a noise, but it's not a noise. If you apply a noise, it doesn't really work. So it's almost look like a noise, but there's no easy way we can actually interpret this. But anyway, that's the magic of phase. But still, it's not a constant. It's not 0. It's something, and it just shows that what these frequency components are at different offset. Cool. So you will pretty much do the same thing. So, look at this. This is essentially what that short-time Fourier transform is doing. So, when you get this thing, pretty much you get everything just messed up together. But now what we are trying to do is that we grab the first 200 millisecond, and now we apply FFT. And hopefully once you've done this, you will see that, well, now it becomes a very clear spectrogram, because you are looking at the first 200 millisecond. That's just one single note. So there's one single pitch. And if you do it correctly, you should be able to see, the frequency. And, think about the frequency. There's a way you can use numpy.argmax to get the peak. And then you turn that peak and look at the, MIDI note number and see what's the pitch is that. And it should be exactly what you listen to. So everything here, if you do it correctly, the answer should just match itself, because you can listen to it and you see what it is, and you can just grab the note. So it shouldn't be too tricky. And then you would do a bunch more, short-time Fourier transform on the browser. And there's a fun part. Surprisingly, last year people didn't get it correct all the time. But spectrogram matching. So just to give you the sense, what you can actually look at these and see what they are. So some hints is that, what's the difference between them? Vacuum cleaner is just pretty much making noise. Trumpet is a harmonic sound. So as I say, harmonic sounds will have harmonics. So you will see those stripes. So you have a fundamental frequency and you will have only the multiples. But for noise, it's pretty much just flat and everything noise. Then what about drum? What's the difference between drum and vacuum cleaner? Is that, drum, you will have that on sets. You click at different, you kick the drum at different places. So vacuum cleaner is pretty much just making the constant noise, but drum kit, you should have see some of those. And drum kit is very interesting because the drum kit, when you have hi-hat, when you have the cymbals, those cymbals are more like noise. But when you do the drum are actually pitched. So it's actually a combination between pitch instrument, even though it's more like drum rather than a specific instrument sound, but it's still pitched. And then you have the noise that will get you impulsive, vertical-ish size. So that's a hint. So you should be able to see what these are, and that's the hint. I think it's obvious enough what I meant. And you just match that. Cool. So that's PA2. Questions? Nope. Then have fun. And PA1 is doing well, right? Like the Google Colab thing. Okay. And PA2, I think you can still just use Google Colab. I think that's the easiest way. We are not using any powerful CPU anyway. The only downside of like Colab is that sometimes it will forget what you have. And when you store stuff, it will be gone. But should be good enough for our case. I would just want to talk about this because I think this is very cool. So this is actually something about AI. So like TLDR, what's going on is like using diffusion models to generate visual spectrograms that look like image, but can also be played as sound. So that's essentially what they are doing. It's actually being done at Andrew Hao-Wen's team, who's at Michigan, but now he's moving to Cornell. But Daniel and Ziyang was here this last semester. So they just graduated, but it's a pretty cool project. So pretty much what you have is that, well, this is, colorization is something beyond, spectrogram, because spectrogram is just no color pretty much. But this is what they generate, and they just also apply a colorization model for that. But anyway, this is what they generate. You have this spectrogram, and it just sounds like your prompt. So you have the audio prompt, it's dog barking, and you have the image prompt as a colorful photo of a corgis. So the diffusion model is trying to morph these two things at the same time. I want this thing to be interpreted as an audio spectrogram that sounds like dog barking, but at the same time, I have this image prompt. It should also look like, when we don't treat it as a spectrogram, it should also look like a corgis. Yeah, and so this image tiger's audio prompt is tiger growing. So you can actually see some of these. These are very speech-like. So we talk about, so actually when you work enough with spectrograms and signals, whenever you see something like this, you can actually tell what type of thing are those. So these are like typical music spectrograms. These are actually typical speech spectrogram, because you see that there are some stripes, but they are, slightly moving around and it's a little bit thicker. That's because the whole vocal system, there's a source filter modeling. So basically you are changing your muscle and the placement of your tongues and the shape of your mouth, so that you constantly changing that frequency combination over time. That's how we get the tones, how we get different vowel, different, consonants. So this is very speech-like. And this one is And you can pretty much already tell there's a very strong lower line and it's pitched. I think it's pretty fun. There's you can see, and this one is the bell tower, and you can see the harmonics. Cool. Anyway, it's not the best in sound quality, but I think it's fun to see that. Well, now you see all those horizontal harmonics at these bell is pitched, so you want to get those. Cool. 5 minutes left. Just quickly recap. Again, now we are doing this, spectrogram mostly in this class. And we started from, sampling rate because, you cannot just capture everything in perfect resolution because there's just no way. So you want to downsample it a little bit. Not downsample, you want to sample it a little bit, depending on how good your microphone is. So if you want to double the sampling rate, then it will be much denser. You can also double the bit depth. It's not double, it's increment the bit depth for one, but you would double the amount of possible Y value you can do. So you can get finer sampling for that. And we talk about this sampling theorem where we talk about Nyquist rate, but pretty much what you want to remember is that, well, we need 2 times that original frequency to capture it, to reconstruct it, to be able to detect it. Because if not, then the way we can sort of like guess from only the answer sample once is something else that we just couldn't recover the original signal. It could be 2 times, it could be 3 times, who knows? So the maximum, the minimum sampling rate needed is 2 times the frequency that you want to detect. So this is what we call sampling theorem, and that's called Nyquist rate. And then we talk about spectral analysis. Just to quickly go over, our goal is just to decompose things into different components. And this is how we do it. You grab a signal, different frequency of signal, and you pass it onto the signal, and you compute the multiplication, multiple of them, and you sum over the whole, blue area minus the red area. So in this case, everything is positive because the 2 hertz thing just perfectly match. So you get a very strong detection. But for 5 hertz, now there's some negative part. For 10 hertz, still some negative part. But overall, it's sum to something. And so this magnitude sort of show you how good the match is, how strong that signal, that frequency component is. And that's how we do this spectrum frequency domain analysis. And for short-time Fourier transform is that we want to go one step further. Now we want to localize where this frequency happen. And so it's pretty straightforward. What we want to do is just like, slide through it. We just get a slice of them, and then we do Fourier transform on each of the slice. And so now you get this thing. So, fundamental frequency, usually when you are analyzing music signal, you will see the fundamental frequency, and you have all the harmonics. Cool. And this is the last one we see, like a very cool example. Cool. And this is a teaser for next week. Should be fun, hopefully, to get some deep learning idea.